So let phi of r equals 1 by 2 pi log r if n equals 2 and minus 1 by n minus 2 alpha n r to the 2 minus n if n is greater or equal to 3 alpha n equals surface measure of the unit ball. So omega in Rn bounded domain and d omega equal to gamma. Let x belong to omega. Define ux equals integral on gamma phi of mod y minus x d sigma y. So this is well defined because you have y will be in gamma, x is in omega, they are not equal, and therefore show that u is harmonic. So solution, so let us take, let bxr be contained in omega. So integral on bxr uy dy is equal to integral on bxr of integral on gamma phi of mod x minus y d sigma y minus z d sigma z dy. Okay, that is the definition because we have to take the u of y is phi of y minus z integral. Okay, now we can, everything is non-negative, so I can or of constant sign, therefore I can interchange the order of integration. This is integral on gamma, integral on bxr of phi of mod y minus z dy d sigma z. So y is in omega, z is on gamma, y is not equal to z, therefore for phi of mod y minus z, y going to this is harmonic. And therefore this is equal to integral on gamma. Since it is harmonic, it is the average. If you take the average on the ball, that will be equal to the value at the center. So this is equal to omega n r power n of phi of mod y minus x, okay, sorry, z minus, it should be z minus x d sigma z. Okay, it is phi of z minus x d sigma x. So integral over y is ball is nothing, the average is equal to value at the center, and therefore that is equal to mod d sigma z, and that is equal to therefore 1 by omega n r power n of integral bxr of uy dy is equal to integral on gamma phi of mod z minus x d sigma z, which is nothing but u of x itself. Therefore u has mean value property, and we know therefore that it means it is harmonic. B, let r be greater than 0, compute integral mod y equal to r phi of mod x minus y d sigma y for every x in Rn mod x less than or equal to r. So, solution. By symmetry, we are on the ball of radius r center origin. This function is radial function and this is symmetric wherever you are. So, this is implies that integral mod y equal to r phi of mod x minus y d sigma y equals constant for all x in Rn mod x equal to r by symmetry. And therefore, and for mod x less than r, harmonic. So, if you call this as u of x, so u of x, delta u of x equal to 0, u of x equal to constant on mod x equal to r. This is 0 if mod x is less than or equal to r, and this is by the previous exercise, and therefore this implies that u is identically constant on mod x less than or equal to r by the uniqueness of the solution to the Dirichlet problem. So, implies that u of x equal to u of 0, and that is equal to integral mod y equal to r phi of r d sigma y. So, if n equals 2, you have, so that is 1 by 2 pi log r into 2 pi r is equal to r log r. If n is greater or equal to 3, so this is equal to minus 1 by alpha n into n minus 2 r power n minus 2 into alpha n r power n minus 1, which is the surface area, and therefore alpha n gets cancelled, 1 r gets cancelled. So, it is minus r by n minus 2. So, that is the 4. Let epsilon be greater than 0, rho epsilon modifier, u Rn to r satisfying mean value property, that is, it is harmonic for every x in Rn. That means you have that u of x equals 1 by alpha n r power n minus 1 integral mod y minus x equal to r u of y d sigma y for every r for every x. Okay. Then show that u equals rho epsilon star u. So, in particular, u belongs to C infinity of r. So, a harmonic function is automatically a infinitely differentiable function. This is true in any omega also. All you have to do is to take whatever proof we are going to do now, we will have to take epsilon such that the ball center x radius epsilon is contained in omega. That is all we have to do, epsilon small enough. Here we are of course at liberty to take any epsilon we like, and therefore the proof is the same. So, this is a proof that it is a regularity statement that if you have a harmonic function, then it is infinitely differentiable in the interior of the domain. Okay, so solution: u epsilon equals u star rho epsilon. So, u epsilon of x will be equal to integral over Rn of rho epsilon x minus y u y dy. you can write it in any way you like, and so I am going to write it like this. So what is that? So that is equal to some k by epsilon power n times integral b center x radius epsilon of rho of mod x minus y by epsilon times uy dy, where rho of z is equal to e power minus 1 by 1 minus mod z square. We call the definition of this. Okay, so this is the definition of rho. Okay, so now if you write this in polar coordinates, this is k by epsilon power n integral 0 to epsilon. Okay, rho, so mod x minus y is r, so r by epsilon integral mod x minus y equal to r. So we have to integrate on the remaining coordinates. So u of y d sigma y dr. So this is polar coordinates. But u is harmonic, so it has mean value property, and therefore this is equal to k epsilon n, sorry, k by epsilon power n. So this will be alpha n of r integral 0 power 0 to epsilon of r power n minus 1 rho of r by epsilon times u of x dr, and that is equal to u of x into k by epsilon power n. In fact, so k by epsilon and r rho by epsilon is just rho epsilon. So and you are multiplying, it's a radial function, into r power n minus 1 dr 0 to epsilon. So that is precisely again b 0 epsilon of rho epsilon of x sorry of y dy, and then and this we know is equal to 1, and therefore this is equal to u of x. Okay, so that proves this thing. A, let V be relatively compact in omega, V omega bounded domains in Rn. Let R equals 1 by 4 d V from gamma, gamma equals d omega. Let xy belong to V, mod x minus y equal to R. Let u from omega to R be a non-negative harmonic function. Show that u of x is bigger than or equal to 1 by epsilon power, sorry, 2 power n u of y. So solution. So we have xy in V, mod x minus y equal to R. Okay. Now u is harmonic, so u of x is equal to 1 by omega n r power n, sorry, 2 power n r power n. This is the volume of the ball of center x, radius 2r, okay, and u of z dz. Now u is non-negative, therefore I can write this as greater than or equal to integral 1 by omega n 2 power n r power n integral b yr uz dz. Okay, so this is because it's harmonic, and so this is harmonic. So you have mean value property, and this is because u is greater or equal to 0. So you have a ball of radius 2r, so this is x and this is 2r, and then you have y here, and therefore a ball of radius r is contained in that. Okay. But what is that? Again, by the mean value property, this is equal to 1 by 2 power n u of y. Again, mean value property. Okay. So ux is greater or equal to 1 by 2 power n u of y. Similarly, you have u of y will be similarly 1 by 2 power n u of x, and therefore you have that 2 power n u of y will be greater or equal to u of x greater or equal to 1 by 2 power n u of y. Okay, so that means you can always compare values between 2 points with some which are close enough. Okay, so B is called Harnack's inequality. U greater or equal to 0 harmonic in omega, and V relatively compact in omega, then there exists a C subdomain. Okay, this is omega, this is bounded domain, which means it is connected. Okay, there exists C greater or equal to 0 depending on V, such that 1 by C u of y less or equal to u of x less or equal to C times u of y for every x y in V. So, in particular you have that sup of u over V is less than C times inf over u of u over V. Solution. So, V is compact, okay, V closure is compact, and therefore can be covered by a chain of finitely many balls Bi I equals 1 to k, each of radius r as above, as in A, r as in A, okay, and Bi intersection Bj, Bi plus 1 not empty. So, you cover it like this, okay, and you have x in B1 and y so, in each of these balls you have 1 by 2 power n, there are at most k balls. That means if xy belong to V, then u of x will be greater or equal to 1 by 2 power n times k times u1, and that will give you the result. Okay, so this five A omega in Rn bounded open set gamma equals d omega f in L2 of omega and u belongs to h1 of omega intersection c of omega bar such that integral on omega grad u dot grad v dx plus integral on omega uv dx equals integral omega fv dx for every v in h1 0 of omega. That means it satisfies the differential equation in the sense of distribution, because we can take v in d omega and but we do not know anything about the boundary conditions, because v is in h1 of omega and u is in h1 of omega and v is only in h1 0 of omega. Show that minimum of inf u over gamma inf f over omega is less than or equal to ux less than or equal to max of sup u over gamma sup f over omega for every x in omega. So, solution, you have take m equals min of inf u over gamma inf f over omega. Then u minus m belongs to h1 of omega, there is no problem about that. Okay. So, you have integral grad u minus m grad v plus integral u minus m v equals integral f minus m v. Okay. So, now you take v equals u minus m minus this belongs to h1 0 of omega, because m is less than the infimum of u. Okay. So, u minus m will be greater or equal to 0 on omega. So, minus will be there and therefore, you will get this minus integral, we have seen this before, grad u minus m minus square on omega minus integral mod u minus m minus whole square on omega equals integral f minus m u minus m minus on omega. Now, f minus m is non-negative. Okay. So, this is also non-negative. So, this everything is non-negative and this side everything is less than or equal to 0 and therefore, you have equal to 0 and this implies that u minus m minus equal to 0 implies u equals m. So, similarly, you take capital M equals max of sup u over gamma and sup f over omega, and then you look at the function m minus u and show that that is greater or equal to 0 by the same argument, and you can do it. B, if f equal to 0, show that mod u 0 infinity omega is less than or equal to mod u 0 infinity gamma. So, solution, f equal to 0 implies both u and minus u satisfy star. So, you have u of x is less than or equal to sup u over gamma, which is less than or equal to mod u 0 infinity gamma, and then you have minus u of x is less than or equal to sup minus u over gamma, which is again less than mod u 0 infinity gamma, and therefore this implies that mod u x is less than or equal to mod u 0 infinity gamma, and this implies that mod u 0 infinity omega is less than or equal to mod u 0 infinity. 6. Let omega equal set of all x in Rn such that mod x is bigger than 1. So, you are taking the exterior of the unit ball. So, unit ball is here and then this is omega, okay, and let u is in h1 of omega. Then minus Laplacian u plus u equal to 0 in omega. Show that mod u 0 infinity omega is the same to mod u 0 infinity gamma. So, this is like the previous theorem, only a problem except that we have an unbounded domain. So, you take omega n to be equal to set of all x in Rn such that 1 is less than mod x less than n. Okay, so now this becomes omega n. Okay, so that is now a bounded domain, and therefore you have that. So let gamma n equals set of all mod x equal to n. Okay, so mod u 0 infinity omega n by the previous exercise by 5 b, this is less than or equal to max of mod u 0 infinity gamma. So, gamma is mod x equal to 1, okay, and mod u 0 infinity gamma n, okay, and then u is in h1 of omega implies mod u 0 infinity gamma n will go to 0 as n tends to infinity, because the function, if it is in h1 of omega, it has to vanish at infinity. It cannot, it has to go down to 0, as you, because you know that it is it's a L2 function and so on. So, it cannot be positive on a set of positive measure as the domain grows. Okay. Okay, so as this thing, and also mod u 0 infinity omega n will go to mod u 0 infinity omega. Okay, from this you conclude that hence the result.